Welcome back. So today, I'm going to be talking mostly about measurement. And I'm going to be talking about what it means to take a measurement or expect to take a measurement. But I want to do so by thinking about our operators and our eigenstates in a bit more of a general way. So you're used to me seeing this expression, right? After all, we started with the Stern-Galick experiment where we had a system that had two different eigenstates. And I had, therefore, two different coefficients, alpha and beta, that represented the probability amplitudes of the first and second eigenstates. So I want to challenge us today to take that notation and sort of promote it to the notation of a system that has an unknown number of eigenstates. Here I'm going to have a system of I different basis vectors, right? So I shouldn't say I, that's an index, but n different basis vectors. And therefore, for each of the basis vectors, I'm going to have a probability amplitude. And since I don't know how many there are, I'm just going to write that as some sum over I, right? So my basis vectors are indexed by I, and I'm going to have a set of coefficients there, the expansion coefficients, and then I'm going to sum over all of them. Okay, and so for a general space, I can write a state as a sum over the basis, right, times the expansion coefficients. Of course, as we've said many times, in order to have a basis, right, in order to have a set of eigenstates over which I can decompose my state, I need some operator. And so when I talk about a general operator today, I'm going to call it A. Capital A is the operator. And little a sub I are going to be all of the different possible measurements that I can get with that operator A. Each of those measurements has a corresponding eigenvector, which we're going to call phi sub I, and a corresponding probability amplitude, which we're going to call alpha sub I. And I'm going to use the otherwise normal assumptions of quantum mechanics that when I write down this state, it's a nice normalized state and all of that. Okay, so that's the notation that we're going to use. And as I said, we're going to be talking about measurement. And so I'm going to frame today's discussion on trying to answer the question, what is the z component of S, right? So what is the measurement of some operator? And of course, now that you've been in quantum mechanics for a couple of weeks, so the first response that you're always going to give to this question is, I don't know, right? Or really better, be more specific, right? Because when we're talking about quantum mechanics, we already know that we're never going to be able to take some unknown state and talk about characteristics of that state until we measure it. And of course, measuring the state changes the state, right? And so if we're going to ask the question about some measurement of an operator, we're going to have to be very careful about what we mean by the answer to that question, right? And so there are different ways of answering what's the measurement of that operator. The one that you already know is to give the total amount of information, right? Give all the information you can. Well, I don't know what the measurement is going to be, but I know that these are the possible measurements, right? I might get a sub 1, I might get a sub 2, I might get a sub 3, and I can calculate the probability of getting each one of those measurements, right? And that's a lot of information for a general operator because for each of the possible measurements, you're going to have a probability corresponding to that measurement. It's totally truthful, right? In the sense that if I ask you what is the z, what is the z component of the spin, you can say, well, it's 50% chance it's going to be up, a 50% chance it's going to be down. That is a complete answer that tells me a lot of information about what the possible measurements are. Of course, to get any of those answers, I'm still going to have to destroy the state when I actually do the measurement, right? And so we've already dealt with a lot of those sort of conceptual problems with this, and I won't dwell on it, but that is the complete answer. So this amount of information, though, you start to look at it and you say, well, if I know, A1 30% of the time, A2 5%, if I know all of these, I might be able to give you some rough estimate for what you might expect the state to look like, or that is what you might expect the energy to be. Maybe I can just give you one number that can kind of sum up literally all of the information about any of the particular individual measurements. And that's the idea of the second answer to this question, which is, what do you expect the measurement to be? Right? And this is a different way of answering the question because I'm never going to take the measurement, right? If I actually take the measurement, then I end up with only one of the finite possible answers that I get from the operator, right? I'm in an eigenstate, and I have that eigenvalue, and I get the measurement associated with it. Here, we can say, well, before we measure the state, I can give you some sort of idea of what that measurement could be by taking this sum over all of the probabilities of a particular measurement times that measurement, right? And that's, it's like a weighted average, right? 20% of the time it's going to be in this, plus 30% of the time it's going to be in that, plus 50% of the time it's going to be in that, gives me some sort of average idea for what the outcome of the measurement could be, right? And again, this is statistical, right? Because it's probabilities times measurements. And so this is not what the measurement is actually going to be, right? But it contains now a digested amount of information about the state that helps me to understand what the measurement could be, or what the, or what could I possibly expect. And because it's kind of like what to expect, right? It's before the measurement. This quantity is called the expectation value, and I generally put it in these pointy brackets, okay? And you probably have seen these pointy brackets meaning a couple of different things. Sometimes it means average. And that's really what I want to think about this as. It's sort of like, what does the average measurement look like, right? And again, that's a statistical statement, right? And therefore it's one that has to do with these probabilities. Now, thinking about it as the sum of the probabilities times the different measurements is fine, right? But I also know that the probabilities are the modulus squared of the probability amplitudes. And now I can do a little bit of algebra with this, or I can do a little bit of replacement to see if there's another way of calculating what this expectation value is without having to write out all of the different probabilities, right? Without having to do it all, by hand. Well, I guess we'll have to do it by hand, but without having to do it sort of in a brute force way. I know that these probability amplitudes, these expansion coefficients, are just the decomposition of my full state, right, which is psi, onto each of my basis vectors. And so where I see an alpha sub I can replace it with the quantity phi sub I dotted with psi, dotted with my state, right? That's the decomposition. The complex conjugate of that is going to be the reverse, right? And so I can take that dot product and I can switch the bras and the ket and I get the complex conjugate of it and I get this expression. Now a sub I in here is just a scalar, right? And so I can sort of creatively choose where to put that scalar. And what I'm going to do is I'm going to move it in the middle of the first inner product. Now this seems at first glance like a ridiculous thing to do. But once I do it, I notice that this combination here is an eigenvalue times a basis vector, right? And the whole point of eigenvalues is that usually, right, I replace an operator times an eigenvector to get an eigenvalue times an eigenvector. I can do that in reverse here, and so I can take my eigenvalue times an eigenvector, and I can replace it with the operator times the eigenvector. That's just the eigenvector. That's just the eigenvalue equation. And so I've used this to now take away the measurements and replace it with the operators. And, at one point, but Tom, you had these great things. You had probabilities, and you had probability amplitudes, and you had measurements. And now you've taken all of that away, right? The way that we've written it here, there's no more, now there's not even an eigenvalue. Well, okay, maybe it looks more complicated until you remember what we talked about with outer products, in that now I have this whole set of outer products of all of the eigenstates summed over all of the eigenstates, and of course that's just the identity matrix, right? Which means I can take it away and I get this expression. And this is what I think about, or this is what I'm actually going to calculate when I do an expectation value. I'm going to take my operator and I'm going to squeeze it in between the bra and ket versions of my state. And when I do that, then I get out exactly this idea of what do I expect that state to have as a measurement corresponding to that operator, right? Because the expectation value of the operator, and this is one of the reasons that this notation here, moving way up to the left, that notation there can be a little bit misleading because there's no state in it, right? But there is a state in it. I can't take the expectation value of an operator without a state, right? And so when I write it like this, as I do on the bottom, you can see explicitly how I'm going to take the states, put the operator in the middle, and then I'm going to get out the expectation value. Okay. So this is how you actually calculate it. By taking your operator and squeezing it inside a broad set of your states, and then doing out whatever operation it is you need to do out, whether you're going to do it in a basis independent way or whether you're going to do it in matrix notation. So for that, I want to do an example. As I said, sort of callously, quickly a moment ago, you could do this in a basis independent way, or you can do this with matrix notation. Let me do it in both of those ways for us now, right? Sort of as a reminder of what this means. So the first way I'm going to do it is in the so-called basis independent way, and that is I have my operator squeezed in between two copies of my state. Now note, when I turned my ket vector, which is a column vector, into a row vector, I had to remember to take the complex conjugate. And since my second coefficient here has an I in it, that meant when I flipped it up that it turned into a minus I. And that's a step that we have to remember when we're turning a ket into a bra. We always have to take the complex conjugate. Okay, so now because I've decomposed this into the z basis, I have Sz, which will now act on two eigenstates of Sc. And so I can use that operator times the eigenstate with the eigenvalue equation to replace it with the measurements. Okay, I said that awfully fast, but of course Sz times plus is going to give me h bar over 2 times plus, and Sz times minus is going to give me minus h bar over 2 times minus. Okay, now let's actually do it. So I'm not going to do anything with the first state yet. So I have 1 over root 10 plus minus 3i over square root 10 minus, right? But now I can actually act that Sz on the two states in the parentheses. So for the first one, I have 1 over root 10. I have h bar over 2 because that's the measurement for plus. And then in the second term, I have Sz acting on minus, and so that's going to give me a minus 3i over the square root of 10 times h bar over 2 times minus. And now, really, I have these two binomials, right? And I want to multiply them together. I need to FOIL it out, of course. But since I've got a good orthonormal basis, that foiling results yet only in two terms. The first one when I have the plus times the plus, and therefore I have the coefficient in the first one times the coefficient, that's going to give me a 1 over 10 times h bar over 2 plus plus. The only other term that survives is going to be the multiplication of the other two. Now this is hard, so minus times minus is a 1, but an I times an I is a minus. So I have minus, 3 times 3 is 9 over 10 h bar over 2 minus minus. These things are both 1, right, because of the orthonormality. And now, let's see. Okay, so 1 over 20 minus 9 over 20 gives me minus 8 over 20, which is minus 4 over 10 times h bar. Okay, and therefore the expectation value of Sz when I do it like this is minus 4 over 10 h bar. And you can see that that is neither minus h bar over 2 or plus h bar over 2, right? But it somehow tells me, well, you can expect it to be kind of negative because more often than not, because the second expansion coefficient is bigger, right, in modulus, you're gonna end up with the negative state more, right? And so this is sort of it's the weighted average of what's going to happen to this state when you measure it. This is the basis independent way. Let me quickly do it now in the matrix notation way. And I like this because it's it's just a different way of doing the same problem. In this case, I can actually construct the row vector for the first thing, right? Because the row vector for plus is 1, 0, and the row vector for minus is 0, 1. And so the thing that I get over here is 1 over the square root of 10. And then in the second entry, I have minus 3i over the square root of 10. My SZ operator is 1, 0, 0, minus 1. And then on the right, I have 1 over the square root of 10 times. And then on the bottom, 3i over the square root of 10. And now it's matrix multiplication, right? So let me act the matrix on the second one. 1 over the square root of 10 minus 3i over the square root of 10. Oh, did I forget my h bar over 2? Man, h bar over 2. And then now I'm going to do the matrix multiplication out. That switches the sign. Well, that's good because I would have been worried if I didn't get the same sign out. Now it actually just looks like a dot product, and well, I'm going to get the same thing, right? Minus 4 over 10 h bar. And it's just a different way of doing the same problem, right? If you like to do the matrix multiplication, this way is really cool. If you like to do it in the basis independent way, the other way is really cool. Okay? And that's what gives me the expectation value. Now, the expectation value, of course, is a mean, right? It's an average, it's statistical. And therefore, you might ask yourself, well, how certain are you that that expectation value corresponds to what the measurement's going to be? Like, isn't there, because of the fact that this is a statistical quantity, isn't there some uncertainty, right, associated with that? And there's a couple of ways of quantifying this. Usually, the first thing I go to is called the variance, right? Which is gonna give me some, it's gonna give me a measure for how much wiggle is there in that measurement, right? How certain could I be that I'm gonna get the expectation value? And this is defined now to be the expectation value of the square of the operator minus the square of the expectation value of the operator. Okay, and so it's basically saying, well, it's the variance, right? It's saying if you square your data minus the data square, you're going to get minus the mean squared. Then you're going to get some idea of how far away are your measurements from the mean, right? Which is the definition of the variance. Now I can do it for the problem that we just had, and I'm going to do this a little bit faster, and I'm going to do it in matrix notation just because that's how I started writing it out. So I already know what the expectation value of SZ is for this state. So in order to calculate the variance, I need to know what the expectation value of SZ squared is. And so the SZ squared operator, well, it's just 2 copies of SZ, which is going to give me, let's see, I got an h bar over 2, h bar squared over 4, right, because there's one from each. Now I'm going to do this matrix. Oh, look, it's the identity matrix. Awesome, right? And so it turns out if I squeeze this in between 2 of my states, right? So I'm going to find the expectation value of SZ squared. If I squeeze this in between 2 of my states, I'm going to have 1 over the square root of 10. Don't forget to take the complex conjugate, minus 3i over the square root of 10 times h bar squared over 4. Now, the identity matrix is not going to do anything to my other state. Minus, plus 3i over the square root of 10, right? And so now the identity matrix acting on that state is the identity matrix. I'm just going to get rid of it, right? And I'm going to do now a different type of dot product. I have h bar squared over 4. Now I have 1 over the square root, 1 over 10. Now it's going to be, there's a minus sign and there's an I, so it turns to a plus. Well, that's plus 9 over the square root of 10. 1 plus 9 is 10. Over 10 is 1. And I'm left with just h bar squared over 4. Now, that's actually really interesting, right? So the uncertainty in SZ, or the expectation value of SZ squared, well, it actually seems like it's always going to be h bar squared over 4, right? Because if SZ squared is proportional to the identity, then that's that. Just maybe you remember that. I don't know. Anyway, this is what it is, okay? And so I can calculate the variance now of this state by taking SZ squared minus SZ squared, and it's good that you're watching me write that, otherwise it sounds ridiculous. So it's going to be h bar squared over 4 minus, now I have to square that, so it's 4 squared is 16 over 100. This is beautiful, isn't it? H bar squared. Oh, I really should have brought a calculator with me. Okay, so times 25 times, make this 100 down here, the denominator. 25 minus 16, that one I should be able to do, right? That's 9. 9 over 100 h bar squared. Huh. Well, that's something. Although its units aren't right? So the variance is an important quantity of how far away things are, but it still, it has units of h bar squared. If I want to compare that to the mean, well, there's this idea of actually calculating the standard deviation, right? Actually calculating the uncertainty, which is the square root of this. So let me just finish doing it for this operator. It's going to be the square root of 9 over 100 times h bar. Square root of 9 is 3, square root of 100, 3/10 h bar, right? And that again is now going to tell me, well, how uncertain is my answer, right? So I could even now write it down in Kenyanist form, right? So what is the z component of SC going to be? Well, it's going to be minus 4/10 h bar plus or minus 3/10 h bar. Right? And so that gives us some idea for, and I guess it's not Kenyan form because there are no equal signs. But anyway, it gives me some idea for how certain I am with that answer. Okay, I've gone on for a while, so let me wrap up. There are different ways to ask how a measurement is taken. And practically speaking, right, we've gone through how to do this by taking the expectation value, which gives me one number associated with sort of the weighted average of the state, right? So the expectation value is about some state, not about what happens to that state after you already have taken the measurement, right? This is what do you expect the measurement to be sort of in general. And then if you want to talk about how certain you are, you can talk about the variance, or you can take the square root of the variance and you can get the actual uncertainty. And that gives us an idea for how to quantify what a state might look like before I take the measurement. Okay, see you soon.